Hi, hi everyone, welcome to your YouTube channel Engineering Choice. And today we will going to discuss about the elongation and the stresses in the bars of a uniformly tapering circular section. So here we will discuss only the derivation for the change in length. In next video we will discuss about the derivation for the elongation and the stresses in the bars of uniformly tapering section bus, that is rectangular section. Okay, and then we will discuss some numerical on these two topics. So I request everyone, please like this video, then hit on bell icon and the subscribe this channel. So I am planning to upload all the videos which are related to structural subject in the civil engineering, like engineering mechanics, strength of material, structural analysis, design of steel structure, design of RCC, and the design of basic structure. So to get the updates of these videos, please subscribe my channel and hit on the bell icon. So without wasting time, let's get started with today's lecture. So as we discuss today, we are calculating change in length for uniformly tapering circular section. So here we are considering circular section, and that circular section is not a constant from one end to another end. In previous videos we have seen that, or we have focused on the section these are uniform from first end to last end, but now here we are focusing on the tapering section. Tapering section means the dimensions are varying from first to last. Means if you consider any section at any location, so dimension at that location is different as compared to the end and start point of that section. So that particular section is called as a tapering section. And in tapering section there are two types. First is the circular tapering section and second one is the rectangular tapering section. Here in this video we will discuss only about the circular tapering section. So just for this, just consider a taper bar of length L. Now here initially we are considering one bar of L length, means total length of that bar we are considering as a L, and the diameter varying uniformly from D1 and D2 as shown in diagram. So here second thing we are considering diameter, and that diameter is varying from D1 to D1 to D2. So this diameter and the length is shown in diagram. Then next one, take a small differential element at a distance x, length dx and diameter d dash as shown in diagram. So similarly consider one small element, okay, on that particular tapering circular section. So that small element having the distance x from the left hand we can consider, then length of that small section or the element is dx, and the diameter at that small element is a d dash. Okay, so these are the dimensions for the small element of total this circular tapering section. Then next one, in this section diameter of bars are varying linearly from d1 and d2 as we discussed. This section having diameter d1 and d2, and it's linearly varying from d1 to d2. Means d1 diameter we are considering as a small and d2 diameter is a large. And then as usual we are considering one tensile force p1 on the section. Okay, so here the main thing is what we have to calculate the change in length, okay, for this section, and the general formula for the change in length is PL by AE. Okay, general formula is what? PL by AE. Now P is what? P is the axial force acting on the section that we know, P, okay, that we have considered in this section. Then L is the total length of bar. So also we have the total length of that bar L, correct. A is what? A is area of that section. But here if you consider the section is a tapering section, so we have to consider circular tapering section. So area of that circular tapering section is pi by 4. Okay, A is equals to pi by 4 into d square. But now here d is varying from d1 to d2. It means we don't have a fixed diameter of that section. That's why we have considered this small section over here, and we have considered diameter of that small element as a d dash. So we have to calculate this d dash in the form of d1 and d2. So that is our mainly motto or the main aim to calculate the change in length. So here one thing is clear, for the change in length we require P that we have already given in the numerical. L also we know, but we have to focus on the area of the tapering section by considering this small element. So main aim is what? To calculate the area. So let's get start with the calculation of A. So diameter is varying from d1 to d2. So just consider the interpolation formula, that is d2 minus d1 divided by total length. So maximum diameter minus small diameter divided by whole length. Similarly, d dash minus d1. So now here we have considered the small element over here, and that small element having diameter is d dash. So similarly, d dash minus d1 divided by x. But here we require small d, so we convert that equation in the form of d. Okay, so see first. So d2 minus d1 by L is equals to d dash minus d1 by x. So just convert, take this x on the left side. So this will d2 minus d1 by L into x, and the remaining term is d dash minus d. Okay, but here we require d dash. So take this d minus d in right side. So we can write d dash is equals to d2 minus d1 divided by L into x plus d1. So this is our diameter of that small element in the form of initial and final diameter, that is d1 and d2. Now here we have calculated the diameter, but actually we require the area of that element. So now for the cross section area of the differential element, means that small element. So formula for circular section area of circular section is what? Pi by 4 into d square. But now here we are applying that formula for the small element, and the diameter of that small element is d dash. So area for that small element is pi by 4 into d dash square. But d dash is how much? This is our d dash. Okay, so just put d dash is equals to this value, that is d2 minus d1 divided by L into x plus d1 whole square. So this is the area of our circular section. But we require change in length. So formula for the change in length is what? As we discussed in last uh, slide, PL by AE, where P is what? Axial force, that we know. L is what? It is a length of that differential element, because we are applying that formula for the differential element. That's why consider L is a dx, because in the section we have considered the length of small element as a dx. Then a is what? This is pi by 4 d2 minus d1 by L into x plus d1 whole square, and we take as it is. So dx is there, and where we are applying this formula for the differential element. So for the total elongation, means actual elongation, for the calculation of actual elongation or the total elongations, we need to differentiate this equation. Okay, we need to differentiate this equation with respect to x by taking limit 0 to L, because total length of cross section is L. Okay, so just consider 0 to L integration. Put all these equation here. P into dx divided by pi by 4 in bracket d2 minus d1 by L into x plus d1 whole square into E. Now here see, this P and pi by 4 and E, these terms are constant. So take this these all terms out of the integration. So P divided by pi by 4 into E, integration of 0 to L dx divided by this term is as it is. Okay, this term we kept as it is. Okay, now we know the mathematical rule. If any term, let's say suppose a divided by b by c, so denominator to denominator, we can write that term in the numerator, that is ac divided by b. This is a mathematical term. So in the same way, we can consider this 4 as is in numerator. So we can write delta L is equals to 4p by pi e integration of 0 to L dx divided by d1 plus d2 minus d1 by L into x whole square. Also, we know the formula that we have uh, or learned in the engineering mathematics, that is integration of dx divided by x square. We can write that x square like this, x raised to minus 2x, and the integration of x raised to minus 2x is x raised to n minus n. Like this, we know that integration of x raised to n is equals to x raised to n plus 1 divided by n plus 1, like this. But here power of x is minus 2, so it is x is equals to, sorry, integration is equals to x minus 2 plus 1 divided by minus 2 plus 1. So minus 2 plus 1 is a minus 1, and this is also minus 1. So we can write that integration x raised to minus 1 divided by minus 1. So here our total x term is this d1 plus d2 minus d1 by L into x. This is our total x term. So we are while taking the integrations, we are considering this term as the total x term. So we can write this term raised to minus 2 and just take the integration of this term. So integration of this is delta L is equals to 4p by pi e is as it is. Then this is our total x. So integration of this term is d1 plus d2 minus d1 divided by L into x raised to minus 1 divided by minus 1. But now see, this is also one term with the x. So we have to take the derivative of the term. So we know that the derivative of, suppose, ax with the form of x is a. Like this, we have to take the derivative of this term. Okay. So derivative of this d2 minus d1 by L into x square. Okay. Hope you are getting this equation. Okay. Now next, delta L is equals to 4p by AE. Okay. The total term, power of the total term is minus 1. So now we can write that uh, total term in the denominator. So just here we have written that this term in a denominator. Okay. So next one is what? Delta L is equals to 4p by pi e into d2 minus d1 by L into A. So this is a constant term. Okay, this is a constant term. So we have taken that term out of the limit. So remaining term is what? Minus 1 and this one. D1 plus D2 minus D1 by L into x raised to n. Okay. So this is the total term that we have over here. So L and L again in denominator to denominator we can write in the numerator. So that's why we have considered that L in the top. So 4pl by pi e d2 minus d1, and this term is as it is. Now put the limit. Okay, we have the upper limit is L and lower limit is 0. It means we just put the first x is equals to L, then minus x is equals to 0. Okay, so this term is as it is. See, 4pl by pi e d2 minus d1. Now put first limit, that is minus 1 d1 plus d2 minus d1 by L into L. X is L. First upper limit is L, so consider L, minus minus 1, then again same term, but now x is equals to 0. Okay, just put x is equals to 0 over here. So this term will be 0 because this bracket is multiplied by 0. So remaining is only 1 minus d1, and this minus and minus will get plus. Okay, and here L will get cancelled, so remaining term is d1 plus d2 minus d1. Okay, now here here d1 and d1 get cancelled, so remaining term is d2, so minus 1 divided by d2 plus 1 divided by d1, and this term is as it is because it is constant. Okay, similarly we have kept this term is constant over here and here also, and here just we have taken the cross multiplication, that is d1 into minus 1, that is minus d1, and d2 into 1, that is d1, plus d1, sorry, divided by d1 into d2. Okay, so just taken cross multiplication over there, and here d minus d1 plus d2 we can write d2 minus d1, so this d2 minus d1 and d2 minus d1 will get cancelled, and the remaining term is 4pl by a 4pl by pi e into d1 and d2, and this is our final equation for the changing length of circular tapering section, that is 4pl by pi d1 d2 e. So remember this formula for the circular tapering section. So this is the most important formula. If any circular cross section is given, tapering section is given, so you can directly use this formula for the calculation of changing length. Okay, thank you. So in next video we will discuss about the circular tapering section. Here we have discussed the circular tapering section. In next video we will discuss the tapering section, rectangular tapering section, the derivation for the rectangular tapering section. Okay, thank you.